We now move on to module 3. We'll talk about embeddings, specifically node embeddings and tuple embeddings. What do we want to achieve in this module? So first, we want to understand the concept of embedding, also called representation learning. What is its role in machine learning? How is it applied to structure the data? Specifically, we'll study the encoder-decoder paradigm, which is very important, as well as important instantiations of it in the case of structured data, and specifically the common instantiations of random walks and matrix decomposition. Okay, and then we learn how these techniques are adapted to relational databases and to heterogeneous graphs. Okay, so let us begin with the embeddings. Later, we'll talk about node embeddings in the next part. And lastly, embeddings in the context of relational databases. All right, so representation learning and embedding. So the idea is that machine learning models typically operate over numerical representations of data, feature vectors. Okay, these features vectors are not just including the information about the object, they are essentially representing the objects for the machine learning model. If we want to apply such a model to data that doesn't come in this form, we need to come up with this form. We have data that looks like text, graph, database, and we need to come up with a numerical representation for machine learning algorithms to be able to operate over it. Okay. Now, the process is called representation learning, and we can think of it as embedding our entities in the RD Euclidean space. Okay, here we have D dimensions of our embedding. The common view of embedding is something that is general purpose. It's not just for the sake of one specific task, but something that you can reuse in many tasks. That's not always the case. This is not necessary. We'll discuss it later. Okay, so what do we embed? In the context of this course, we are interested in node embeddings. Well, edges can also be embedded. This is more rare. There are also embeddings of whole graphs. I always give this example of molecules that are represented by small graphs. In the context of relational databases, we can think of tuples. This is the most common thing, to embed full tuples. But there are also techniques that embed cells, okay, the cells of tuples, and meta-level information like relation names and attributes that's used for data integration, and we see that in this module. Okay, and you can see the analogy to the world of text, where you have interest or use of embeddings of tokens. Well, that's a usual way that LLMs operate, or words that may comprise of multiple tokens, or full sentences or full documents. Okay, we'll focus mainly on node embeddings and tuple embeddings, but we'll also discuss embeddings of other types. Okay, so here is some visual of that. We have a graph, and then we want to embed every node in our Euclidean space. Here we have 2 dimensions for it to be visual. Two as a special case. It typically can be tens or hundreds of dimensions. In the case of a database, we want every tuple to be embedded in our space. Okay, or in the case of full graph embedding, we have a collection of graphs and we want to position every graph in our vector space. Okay, let's talk about the use of embedding. Okay, how general it is. You can think of using embeddings in different ways. One is task specific. So you have a model that uses a numerical representation, and as part of the model, you also compute your embedding your presentation. Okay, so this is a task-specific representation. It is supervised typically by the examples of your specific task. And then at the evaluation time, you get a new instance, you compute the representation and or you compute the embedding and then you apply the upper layer model. So that's a task-specific representation. I can also think of a task agnostic, where you learn once, okay, and apply it in many different tasks. Now, since you apply it to different tasks, you don't necessarily have training data for any specific task. You don't want to use training data of a specific or a particular task. So what you do is use techniques that are either unsupervised or self-supervised. Self-supervised means that you're producing artificial examples from the data itself, like you're hiding some information and want to guess it back. And we'll see different ways of self-supervision. Okay, now it should be good for all tasks. And then at evaluation time, you use your extract, your retrieve your fixed embedding and apply the learned model. And if you want to assess the quality of your embedding, you can try it on a variety of downstream tasks. So you can see papers that basically propose new embedding techniques and then they try it on different tasks. And also, we'll see some ways of illustrating the quality of the embedding by using some visualization of the embedding in 2 dimensions, like Tisne. We'll see several examples of that. Okay, the third approach is fine-tuning, where you start with the task agnostic embedding, but then you further optimize it to your task. So at evaluation time, you actually apply you start with the fixed embedding, apply your further optimization, and go on with the higher level model. Okay? Now, whenever you look at a model, a proposed model for structured data, that's one of the first questions you might ask yourself. The representation. Is it something fixed or is it something that you learn as part of the training or fine-tuned, which is similar to learn. Okay, it's not always obvious from the description of the new models, but this is definitely something that is important. The embeddings that we're going to look at are going to be task agnostic. Okay, that's the focus of this module. Okay, so how does it look like? You have your data, you have the data items inside it, then you apply an embedding of each one, and this is not related to any task. But then when you get different downstream tasks, then you train models on each specific task using these fixed representations, and then the same fixed representation is fed to different models. Okay, that's how it's used in the end. Okay, and this is an example of a Tisne representation where you basically say, I started with my structured data, like a graph. I compute an embedding, like 256 dimensions, and then I apply some reduction to 2 dimensions to visualize it on the screen. Okay, again using a Tisne, that's a common technique. And then you basically assess what you get visually. Usually there are some additional labels, like the colors here representing something. And then you can ask yourself whether this is an intuitive embedding or not, whether this embedding reflects something in reality, some semantics that you know up front. We'll discuss it more in the next slides. Okay, so what makes an embedding good? Well, for a start, it should encode information that is relevant to all downstream tasks. Okay, we look at task agnostic embeddings. Now, what does it mean? Okay, if you think of some sophisticated encoding that basically encodes everything in a single number, then you're basically lossless, right? You have all the information you need, but is it useful? Well, it's not, because who is going to use it? We need an embedding that is not just informative, but also practical or useful for practical machine learning models. It's robust to nuances. Okay, will favor low dimensions if they do the job, but sometimes we have more examples and more resources, and we may want to increase the dimension of the embedding. But this is something that we should be able to choose. Okay, now, uh, but a guiding principle, for task agnostic embeddings is that the geometric proximity should correspond to the semantic proximity. Okay? For example, if you see here two things that are nearby, then they should be more similar semantically. And if they are far apart, then they should be less similar. If two things mean alike, then they should lie alike. And if they lie alike, then they should mean alike. Okay, here's an example of something that many of you are probably familiar with these computer science conferences. And this is an example of a good embedding, because you see that you don't really care about where each conference is in the embedding in the space, but what you care about is that conferences of a similar topic, the same topic, are nearby. And topics that are closer to each other, like NLP and the artificial intelligence, they are nearby, close to each other in the space, and farther from uh, topics that are um, farther from them, like theory, computer science theory. Okay, so how do we obtain these embeddings? That's actually a very good question. We'll see that there's a rich research around this question. One way is to extract a lot of features, like we saw in the previous module, okay, like many graphlets and so on. And then you can say reduce your space, reduce the dimensionality. How? Well, you can apply feature selection, and we talked about filter methods and wrapper methods and so on. You can apply dimensionality reduction, okay, using linear algebra. That's another approach. The problem with feature-based embedding is that the role of the human in the loop is very significant. It is sensitive to what features you select. Okay, and it means that in every instantiation you need to have the people choosing these features. It is expensive because you want to compute a lot of features to capture everything, right? And also, how does it relate to the semantic proximity? The connection is not direct to semantic proximity, and a common way is to compute an embedding from scratch by optimizing for this proximity. You choose some natural interpretation of proximity and try to find an embedding that best captures this proximity. Okay, so this proximity is also captured by the distance functions called kernel functions. Okay, and as we said, you want your geometric kernel to correspond to the, say, semantic kernel. Okay, and that's what we're going to study in the next parts.